Okay, so the reason that we look at universal gravitation in a unit on circular motion is because it leads really quite nicely to this idea of orbit. We're going to draw a force diagram for mass m in orbit around some planet. So basically the only force acting on this object here is a force of gravity towards m, big M rather. And this guy also has some velocity. So we have an object that's moving around another object, and there's a force inwards in this circle. By definition, we've got an object in circular motion. So an orbit is just circular motion. So let's do a bunch of examples that'll have a bunch of really, I think, quite neat results. So we've got a 10,000 kilogram satellite orbiting 20,000 kilometers above the Earth's surface. We want to find the orbital speed is ultimately what we want to do. So we know the only force acting on this object here is the force of gravity inwards, Fg. We've got a bunch of other data here. We're going to collect off to this side. We know that the radius of our planet is 6,380 kilometers. And we're told that there's another 20,000 kilometers above the Earth's surface. 20,000 kilometers. So when we actually run this through our Fg equation, we need to take into account this total distance from center to center. So we're going to use the radius for our calculation here is going to be 26,380 kilometers. We need that in meters, so that's going to be 2,638,000 meters. Did I do that right? Nope, there should be one more zero. 26,380,000 meters. There we go, that makes more sense. So if we use our circular motion equations on this situation, we're going to get something that looks like this. We're going to have F net C equals MAC, and we know that the acceleration for an object moving in uniform circular motion is given by v squared over r. So the only force inward is Fg, so we're going to get Fg equals m. That little m is the smaller of the two objects. The object actually doing the moving. V squared over r. And so let's plug in our, we know that Fg equals big G mm over r squared. And so we're going to get G mm over r squared equals mv squared over r. We can see here that these little m's are going to cancel. This r is going to cancel with one of those r's, and so what we're going to get here is that gm over r equals v squared. So v equals the square root of gm over r. And now we can actually plug in, we can plug in some values here to figure out what this orbital speed of this object actually is. So we're going to get 6.67 times 10 to the negative 11 times the mass of Earth, which we had to be 5.98 times 10 to the 24 divided by r. So that's 26,380,000. 1, 2, 3, and we want to square root that whole thing. You can verify my calculation here, but I found that v was equal to 3,888 meters per second. This guy right here is a relationship that we want to hang on to. So let's flip the page. So we want to note that the orbital speed is independent of the mass of the orbiting object. It doesn't matter how big that little m is, it ultimately cancels out. We can see here that v, or remember, I guess from the result on the previous page, that the velocity is given by this. Big G, big M over R. M is the central mass. r is the orbital radius, and g is the acceleration. Sorry, g is universal gravitational constant. So there's nothing here dependent on that orbiting mass. We'll show you this proof here. We know that for an object in uniform circular motion, A equals v squared over r. The expression that we just found for the orbital speed, v, is the square root of gm over r. So if I shove that in there, I get that my acceleration is equal to gm over r squared, which is little g. So the result here, it might not be obvious, but what this means is, for an object that's orbiting, it's actually in a state of constant free fall. It's just missing the object in the middle. So if you hate the feeling of falling, don't go to space, because you will have that sensation constantly. Because you are constantly falling towards the Earth, you're just missing it because you have this forward velocity that just keeps dragging you around and around. So an object orbiting is constantly in free fall. Some of you may enjoy that sensation, some of you may not. So you get something that looks like this. Newton imagined standing atop a large mound and projecting a ball horizontally. He knew that balls followed curved or parabolic paths on Earth. So if he threw it, it would fall and drop. If you threw it harder, it would fall, but it would drop further away. If you threw it really, really hard, it would just continuously fall, continuing to miss the planet underneath it. The ball would then be in orbit, and whatever that velocity is, we call actually I don't know if we have a name for it, but that would be the velocity that would be required to get that object into orbit. So the fact that an object is in orbit in orbit is in continuous free fall is interesting, whether you find it that way or not. It means that things in orbit are always falling towards the Earth, even if they never get there. It explains why astronauts seem to float around in a space shuttle or the International Space Station, because the space shuttle doesn't exist anymore, because the passengers and the station are in free fall together at the same rate. So the ship can't actually push back against the people inside. They're both experiencing apparent weightlessness. F and is equal to 0. It means that astronauts experience continuously the feeling of falling, assuming they get used to it. So let's do a classic cartoon example. We have a character kicks a football the wrong way, but the football orbits the Earth and goes through the uprights. We want to know the speed the football would have to move to make it through those uprights, kicking the ball the wrong way. Then we want to figure out how long it takes the football to make the trip, and why this isn't possible on the Earth's surface, but it would be possible on the moon, which is kind of an awesome thought. Here we go. So we know, we're just going to jump straight ahead to this guy. We know that an object orbiting our planet is given by, or the velocity of an object in orbit around our planet is given by v equals the square root of gm over r. We can plug in all the values for gm and r on our planet. We are going to, G is 6.67 times 10 to the negative 11. M is 5.98 times 10 to the 24. And again, I know an upright is a couple meters off the ground, 4 meters off the ground, maybe 16 feet, 15 feet. I don't actually know what that value is. But the Earth is so large. The radius of our planet is so huge. We can ignore those 3 or 4 meters. And so we're just going to use the velocity of our planet. 6,380,000. Did I say velocity of our planet? I meant the radius of our planet. 6,380,000 meters. So, if you plug these values in, you're going to find that you get a velocity here for the football of 7,906.8 meters per second, which is very, very, very fast. In kilometers per hour, just to put that in perspective, That's 28,464.5 kilometers per hour. So you've got a football. The football would have disintegrated a long time ago. But this is the speed a football would have to go to orbit the planet to make its way through those uprights. To figure out how long that's going to take, we're going to use this expression for an object in circular motion. V equals 2 pi r over t. So t equals 2 pi r over v. So we're going to get 2 times pi times 6,380,000 divided by 28,464.5. Oh, sorry, shoot, no, that should be in meters per second. So divided by the 7,906.8, and we're going to get a time of 5,070 seconds, which is 1.4 hours. Basically in 1 hour and 25 minutes, which game's over at that point. So, and the reason this isn't possible on our on the Earth's surface is because the Earth's surface, the altitude varies, or the height of the Earth's surface varies wildly. We've got mountains and valleys and all sorts of hills and stuff all over the place. But it would be possible on the moon because while the moon has large craters, it doesn't have a lot of mountains. You could theoretically, if you placed it right, you could do this on the moon, which would be kind of cool. So conversely, we could use, we could look at something the other way. An example like this: if it takes a satellite 300 minutes to orbit the Earth, then how high is it above the Earth? We've got a whole bunch of expressions here that we're going to make use of here. So I'm just going to write them all out. F net C equals MAC. We've got AC equals V squared over R. We've got V equals 2 pi R over T, and we're going to need FG. That's a comma supposed to be. FG equals GMM over R squared. So we're going to need all of those equations to be able to take a look at a problem like this. We're going to draw it first. There's our planet. Here's the satellite in its orbital path. That's supposed to look a little bit more circular, but I get that it's not. So we know this distance here is 6,380,000 meters. We don't know what this distance here is, that height there. And what we're looking for is the height above the Earth, not the distance to the center. So what we're going to need to find is this x here. When we do the calculation, what we're going to find is this. We're going to find r. So then x is going to be r minus this 6,380,000. But make sure we actually find what the question is looking for. So let's start. This is going to be fun. We're going to start using, as always, the FNet equations and the centripetal acceleration equation. So we're going to get FNet C equals MAC. We're going to plug this guy in there. Now we're going to plug FG over in there. So we're going to get G MM over R squared equals M V squared over R. M's going to cancel. The squared is going to cancel with that right there. And so we're going to get this expression, GM over R equals V squared. We don't want any of those things. What we actually want is T. And so what we're going to do is we're going to take this equation and we're going to plug it in for V. So we're going to get GM over R equals 2 pi R over T all squared. And I'm going to just kick off this way for a second. There's two ways we can go here. I'm going to bring in this squared everywhere here. And so what we're going to get is GM over R equals 4 pi squared R squared over T squared. I'm going to multiply the R up, and I'm going to divide the 4 pi squared down, because that's going to give us a bunch of constants over here. So it's going to give us GM over 4 pi squared. And that's going to equal R cubed, multiply the R up, over T squared. This guy here is what we call Kepler's third law. Really cool result. But ultimately not one that we need a lot in Physics 12. But I'm going to make a note of it down here before we finish this question off. So if we know the period of the orbits, like the 300 minutes we had in the previous question, we can find the radius using Kepler's third law. This nice little result. We get this GM over 4 pi squared equals R cubed over T squared. Something that you'll look at more in university. So let's go back up here. Actually, I'm going to go this way. And we're going to use this result. So we want to figure out what or how high it is above the Earth. And so we're going to get R cubed over T squared equals GM over 4 pi squared. I'm going to multiply the T squared up. So we're going to get R cubed equals GMT squared over 4 pi squared. And then the last but not least, I'm going to take the third root of that, the cube root. It's the cube root of GMT squared over 4 pi squared. And so we can plug in all of our values here. We want to find R, so that's going to be the cube root of 6.67 times 10 to the negative 11. The mass of Earth is 5.98 times 10 to the 24. T is 300 minutes, but we don't want it in minutes, we want it in seconds. So we're going to multiply this by 60. So this is 18,000 seconds. So we're going to multiply this by 18,000 squared divided by 4 pi squared. And we're going to get a value for R, which I'm just going to throw up here. We get that R equals, if you want to do this calculation for me, you'd be welcome to verify it, 14,848,095.9, and that's in meters. To find out, and that's going to be the center to center distance. We don't want center to center distance, we want how high above Earth. So we want this distance here. So then my value for x is going to be this number, 14,848,095.9 minus 6,380,000. We're going to find that x is actually 8,468,096 meters above Earth. Above the surface of Earth, rather. So there you go. That's it for this lesson. I'm going to give you guys some homework to try. I want you guys to look at questions 2 through 4. I want you to look at which ones do I want you to look at? I like 6 is good, 7 is good. And we'll say 9 and 10. As always, if you have any comments, questions, concerns, please let me know via email or by coming to my office hours.